So we've done single traits. Now we're going to do a cross where you're crossing two traits at the same time. So for this one, you need to know Mendel's third law, right? Which is independent assortment. And the law of independent assortment, I'll best say this, the law of independent assortment really says that when there are, or that the alleles, sorry, excuse me, during gamete formation again, the alleles for two different traits sort themselves independently into gametes. And that probably sounds like Greek. So what we need to do is really do an example to explain to you what's going on with that. Now, we already know the first two laws. So the first two laws, remember, we know that you still have the law of dominance going on here. The law of dominance. Remember that that just means that there's two traits for each characteristic, two alleles for each characteristic, and sometimes you have capital letters for them that indicate dominance, and sometimes you have lowercase letters that indicates recessiveness, right? And then the putting together of those alleles for each characteristic determines what the phenotype of an organism is going to be, right? The law of segregation is still working here as well. The law of segregation that just means, and I drew a diagram of this before, is when you're doing a Punnett square and you have a single trait Punnett square, which is fairly easy to do. If you have like this parent here and this parent over here, then during gamete formation, those letters separate into the gametes here and here and here and here, right? That are eventually going to recombine into offspring that are inside the four boxes here, 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 right? So segregation just means that during the formation of sperm and egg, those alleles separate and become single letters, right, here and there. All right. So how does the law of independent assortment fit into that? Well, independent assortment. This is only going to come into play when you're crossing more than one trait at the same time, right? So law of segregation is when you're only crossing one trait, right? Only crossing a single trait. It's dealing with the separation of the alleles from one trait. So with independent assortment, you're crossing two at a time. Okay. So let me take an example here. All right. So for example, plant height, we already know letters for plant height. We've already got that, right? So big T gives you tall, little t gives you short. Simple dominant recessiveness, two alleles, and there they are. What if we add seed coat? Seed coat. Let's say big R gives you round, and a little r gives you wrinkled. Seed coat. There. So two different traits, plant height and the seed coat quality. We're talking about pea plants here, right? And there's the letters that indicate both. So let's say, here's your cross. And as I do this, the law of independent assortment will be better explained, okay? Here's your cross of two parents. Let's say you cross a pure tall and pure round plant with a, let's say, a hybrid or heterozygous, a heterozygous tall, and heterozygous round plant. Oops, sorry. Okay. So let's take that down. I'm getting there. So what would be the genotype for this plant and this plant? Think about that for a minute. Each plant is, instead of having just 2 letters, you're going to have 4 letters for each parent plant. So pure tall would be big T, big T. Pure round would be big R, big R. I could also have said homozygous instead of pure. So there's one parent's letters. Here's the other one. Heterozygous tall means the letters are different. So it would be big T, little t. Still tall, but heterozygously tall. Heterozygous round would be big R and little r. Still round, but heterozygous round. There's my parents. Okay, now here's the question. And this is where a lot of students make mistakes, which is why I want to make sure that you understand what's going on here. When you're making a giant Punnett square for this, let me just make this Punnett square now. The question is, let me make the Punnett square itself. First start with 4 and then divide everything else by 2 again. And again, you don't have to do this. You can just watch me do it. The boxes will be made for you on the worksheet. There. Well, here's the question. If I put, let's say I put the pure parent over here, okay? And I put the heterozygous parent here, okay? What is going to go here, 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 and here? The sperm, right? Let's say this plant is making sperm in its pollen. What letters are going to go in those spots? And what letters over here are going to go in these spots? That's where everybody messes up the first time they try to do this. So these are going to be the gametes, right? The things that go here. So if I have this parent, I'm going to put it over here just to make it more clear. If I have this parent, how do I figure out what gametes are going to go in those 4 spots? And this is what independent assortment, this is where this comes in. You have to combine every T with every type of R to make gametes that are made of 2 alleles each, one of the T's and one of the R's each. So if you remember how to do algebra, remember FOIL? Remember first, outside, inside, last that you had to do algebraically when you were multiplying variables times each other? It's the same principle here. So independent assortment means the big T and the R, the first, combine to make the first gamete, big T, big R. And then first, outside, big T, little r. Inside, little t, big R. And last, little t, little r. I have combined every type of T with every type of R to make 4 different types of gametes that came from this parent. And this right here is independent assortment. I have independently assorted each type of height allele with each type of seed coat allele to make these 4 different types of gametes. Now over here, this parent is completely pure. So yes, we can do the first, outside, and inside, and last, and we can independent assort them, but we're going to get the exact same gamete every time. Can you see that? So that is just a hint that sometimes there is a shortcut to these big dihybrid problems. Yes, did somebody have a question? Sorry, I missed that. Yes, exactly. That's it. It's exactly like multiplying polynomials. FOIL, right? F-O-I-L. That's it. You can apply that here. Excellent, excellent that you saw that. I'm so proud of you for seeing that. Very good. Okay. So now filling in the boxes. Here's my advice to you. When you're filling in the boxes, keep the types of letters together and always write the capital letters, if there are any, first. So if I put 4 letters here, I have a big T and a big T first from here and from here, right? Big T, and big R, big R. Then I'm going to take this next one is, again, big T, big R from the side parent, little r from the top parent, and so on and so forth. Big T, and then 2 big R's. And then big T, little r, big R, little r, right? And then if you're very clever, you could see that all of the rest of these are going to be exactly the same. And I could fill them all in, but they're the same. They're going to be the same because all of these going down are the same. So then when you're doing your outcomes, what percent are going to be tall and round? And a question. How many of the offspring of these parents are going to be tall and round? Meaning they have to each have at least one big T and one big R, right? 100%. That's it. 100% of them are tall and round. Yes. There is no other phenotype here. On the other hand, what percent, sorry, I didn't write that very well. What percent of them are going to be completely heterozygous like this? Are going to have that genotype? Just that genotype. So you should say 25% because only this one, only these, right, are going to have that heterozygous genotype, right? But all of them, no matter what the genotype, are going to have the phenotype of being tall and round. Okay, so that should give you enough for right now for how to do the actual worksheet.